spatial data analysis. Objectives. In this chapter, we will discuss about various aspects of the spatial analysis like introduction to spatial analysis, the building blocks for spatial analysis, using GIS for spatial analysis, geostatistical tools for spatial analysis. Geospatial analysis provide a distinctive perspective on the world, a unique lens through which to examine events, patterns and processes that operate on or near the surface of our planet. The domain of geospatial analysis is the surface of the earth, extending upward in the analysis of topography and the atmosphere and downwards in the analysis of groundwater and geology. In scale, it extends from most local when archaeologists record the location of pieces of pottery to the nearest centimeter or property boundaries are surveyed to the nearest millimeter to the globe in the analysis of sea surface temperature or global warming. In time, it extends backward from the present into the analysis of historical population migration, the discovery of patterns in archaeological sites or the detailed mapping of the movements of continents and into the future in attempts to predict the tracks of hurricanes, the melting of the Greenland ice caps or the likely growth of urban areas. Methods of spatial analysis are robust and capable of operating over range of spatial and temporal scales. Ultimately, geospatial analysis concerns what happens and makes use of geographic information that links features and phenomena on the earth's surface to their location. This sounds very simple and straightforward, and it is not so much the basic information as the structure and arguments that can be built on it that provide the richness of the spatial analysis. In principle, there is no limit to the complexity of spatial analytic techniques that might find some application in the world and might be used to tease out interesting insights and support practical actions and decisions. In reality, some techniques are simpler, more useful and more insightful than others. Spatial analysis exists at the interface between human and the computer, and both play important roles. The concepts that human uses to understand, navigate and exploit the world around them are mirrored in the concept of spatial analysis. The building blocks for any form of spatial analysis are a set of basic primitives that refer to place or the places of interest, their attribute and their management. Place. At the center of all spatial analysis is the concept of place. The earth's surface comprises some 500 crore square kilometer. So, there would be room to pack 500 million industry sites of 1 square kilometer each, assuming that nothing else required space and that the 2/3 of the earth's space that is covered by water was as acceptable as the 1/3 that is land, and 500 trillion sites of 1 square meter each, roughly the space occupied by a sleeping human. People identify with places of various sizes and shapes, from the room to the parcel of land, to the neighborhood, the city, the country, the state or province, or the nation state. Places may overlap as when a watershed spans the boundary of two countries, and the places may be nested hierarchically as when countries combine to form a state or province. Places often have names and people use these to talk about and distinguish between the places. Some names are official having been recognized by national or state agencies charged with bringing order to the geographic names. In US, for example, the Board of Geographic Names exists to ensure that all agencies of the federal government use the same name in referring to the place, and to ensure as far as possible that duplicate names are removed from the landscape. A list of official sanctioned names is termed as gazetteer. Through that word has come to be used for any list of geographic names. Places change continually. As people move, climate changes, cities expand, and a myriad of social and physical processes affect virtually every spot on the Earth's surface. For some purposes, it is sufficient to treat place as if they are static, especially if the processes that affect them are comparatively slow to operate. It is difficult, for example, to come up with instances of the need to modify maps as continents move and mountains grow or shrink in the response to earthquakes and erosion. Attribute. Attribute has become the preference term for any recorded characteristics or property of a place. A place name is an obvious example of an attribute, but a vast array of other options have proven useful for various purposes. Some are measured, including elevation, temperature or rainfall. Others are the result of classification, including soil type, land use or land cover type or rock type. Government agencies provide a host of attributes in the form of statistics for places ranging in size from countries all the way down to the neighborhood and streets. The characteristics that people assign rightly or mistakenly to places such as expensive, exciting, smelly or dangerous are also examples of attributes. Attributes can be more than simple values or terms, and today it is possible to construct information system or contain entire collection of images as attributes of hotels or recordings of birdsong as attributes of natural areas. But while these are certainly feasible, they are beyond the bounds of most techniques of spatial analysis. Objects. In spatial analysis, it is customary to refer the place as object. In studies of roads or rivers, the objects of interest are long and thin and will often be represented as lines of zero width. In studies of climate, the objects of interest may be weather station of minimal extent and will often be represented as points. On the other hand, many studies of social or economic patterns may need to be considered two-dimensional extent of places, which will therefore be represented as areas, and in some studies where elevation or depth are important, it may be appropriate to represent places as volumes. To a spatial statistician, these points, lines, areas or volumes are known as the attribute spatial support. Each of these four classes of objects have its own techniques of representation in digital system. The software for capturing and storing spatial data, analyzing and visualizing them and reporting the results of analysis must recognize and handle each of these classes. But digital system must ultimately represent everything in a language of just two characteristics, 0 and 1 or off and on. And spatial techniques are required to represent complex objects in this way. In practice, points, lines and areas are most often represented in the following standard forms. Points as pairs of coordinates in latitude, longitude or some other standard system. Lines as ordered sequence of points connected by a straight line. Areas as ordered rings of points also connected by straight lines to form polygons. In some cases, area may contain holes and may include separate islands, such as in representing the state of Michigan with its separate upper peninsula or the state of. This use of polygon to represent areas is so persuasive that many spatial analysts refer to all areas as polygons, whether or not their edges are actually straight. Maps. A geographical locational area is represented in the form of geographical maps. These maps are being prepared or surveyed by respective government departments. These maps are providing the spatial look of the real-time objects on the surface. These maps provide an outline or they provide a navigational support to these landforms. These landforms and these maps can be used in different GIS spatial analysis. The maps provide a spatial analysis of how the land is being converted from past to how the land can be converted into future. For example, India before independence, there was Pakistan and India were together in the form of one single map. But after independence, two different maps have been created, and with the respective of states, the number of states have been divided, and accordingly the number of maps are showing the respective boundaries of different states. Network. They include streets, roads, railroads and highways, rivers, canals and streams, and the more abstract interpersonal networks studied by the sociologist. Networks constitute one-dimensional structures embedded in 2 or 3 dimensions. Discrete point objects may be distributed on the network, representing such phenomena as landmarks or bridges on the road networks or observation points on the rivers. Discrete line objects may also be found in the form of tunnels, stretches of highway with a constant number of lanes or river reaches. Continuous field may also be distributed over the one-dimensional network, defining such variables as travel speed, railroad gradient, traffic density or the stream velocity. Mathematically, a network forms a graph, and many techniques developed for graph have application to network. These include various ways of measuring a network connectivity or of finding shortest path between pairs of points on a network. Geographic analysis allows us to study and understand the real world processes by developing and applying manipulation, analysis criteria and model N to carry out integrated modeling. These criteria illuminate underlying trends in geographic data, making new information available. A GIS enhances this process by providing tools which can be combined in meaningful sequence to reveal new or previously unidentified relationships within or between the data sets, thus increasing better understanding of the real world. The result of geographic analysis can be commercial in the form of maps, reports or both. Integration involves bringing together diverse information from a variety of sources and analysis of multi-parameter data to provide answer and solution to defined problems. Spatial analysis is a vital part of GIS. It can be done in two ways. One is a vector based and the other is a raster based analysis. Since the advent of GIS in the 1980s, many government agencies have invested heavily in GIS installations, including the purchase of hardware and software and the construction of mammoth databases. Two fundamental functions of GIS have been widely realized: generation of maps and generation of tabular reports. Indeed, GIS provides a very effective tool for generating maps and statistical reports from a database. However, GIS functionality far exceeds the purposes of mapping and report compilation. In addition to the basic functions related to automated cartography and database management systems, the most important uses of GIS are spatial analysis capabilities. As spatial information is organized in a GIS, it should be able to answer complex questions regarding space. Making maps alone does not justify the high cost of building a GIS. The same maps may be produced using a simpler cartographic package. Likewise, if the purpose is to generate tabular output, then a simpler database management system or a statistical package may be a more efficient solution. It is the spatial analysis that requires the logical connections between the attribute data and map features and the operational procedures built on the spatial relationships among map features. These capabilities make GIS a much more powerful and cost-effective tool than automated cartographic packages, statistical packages or database management system. Indeed, functions required for performing spatial analysis that are not available in either cartographic packages or database management systems are commonly implemented in GIS. Using GIS for spatial analysis. Spatial analysis in GIS involves three types of operations: attribute query, also known as non-spatial or spatial query, the spatial query, and the generation of a new data sets from the original database. Burrow, 1987. The scope of this spatial analysis ranges from a simple query about the spatial phenomena to complicated combinations of attribute queries, spatial queries, and alternation of original data. Attribute query. This requires the processing of attribute data exclusive of spatial information. In other words, it is a process of selecting information by asking logical questions. Example, from a database of a city parcel map where every parcel is listed with a land use code. A simple attribute query may require the identification of all parcels of specific land use type. Such a query can be handled through the table without referencing the parcel map, because no spatial information is required to answer this question. The query is considered the attribute query. In this example, the entities in the attribute table that have land use codes identically to the specified type are identified. Spatial query. This involves selecting features based on location or the spatial relationships, which requires processing of spatial information. For instance, a question may be raised about parcels within 1 mile of freeway and each parcel. In this case, the answer can be obtained either in the form of hard copy map or by using a GIS with the required geographic information. Example, let us take one spatial query where a request is submitted for rezoning. All owners whose land is within a certain distance of all parcel may be rezoned must be notified for public hearing. A spatial query is required to identify all parcels within the specified distance. This process cannot be accomplished without spatial information. In other words, the attribute table of the database alone does not provide sufficient information for solving problems that involve location. While basic spatial analysis involves some attribute queries and spatial queries, complicated analysis typically requires a series of GIS operations including multiple attribute and spatial queries, alternation of original data, and generation of new data sets. The method for structuring and organizing such operations are a major concern in spatial analysis. An effective spatial analysis is one in which the best available methods are appropriately employed for different types of attribute queries, spatial queries and data alterations. The design of the analysis depends on the purpose of study. GIS usage in spatial analysis. GIS can interrogate geographic features and retrieve associated attribute information called identification. It can generate new set of maps by query and analysis. It also evolves new information by spatial operations. Hence, are described some analytical procedures applied with a GIS. GIS operational procedure and analytical tasks that are particularly useful for spatial analysis include single layer operation, multiple layer operations, spatial modeling, geometric modeling, points pattern analysis, network analysis, surface analysis, raster grid analysis. Geostatistical tools for spatial analysis. Geostatistics studies spatial variability of recognized variables. Variables that have an attribute value in a location in 2 or 3 dimensional space. Tools to categorize the spatial variability are spatial autocorrelation function, variogram. A variogram is a calculated from the variance of pairs of points at different separation. For several distances, classes or lengths, all point pairs are identified which matches that separation and the variance is calculated. Repeating this process for various distance classes yield a variogram. These functions can be used to measure spatial variability of a point data, that also of map or images. Spatial autocorrelation of a point data. The statistical analysis referred to as spatial autocorrelation examines the correlation of a random process with itself in space. Many variables that have discrete values measured at several specific geographic positions, that is, individual observations, can be approximated by dimensionless points, can be considered random processes and can thus be analyzed using spatial autocorrelation analysis. Example of such phenomena are the total amount of rainfall, toxic element concentration, grain size, elevation at triangulated points, etc. The spatial autocorrelation function shown in a graph referred to as spatial autocorrelogram, showing the correlation between a series of points or a map and itself in different shifts in space or time. It visualizes the spatial variability of the phenomena under study. In general, large number of pair of points that are close to each other on average have a low variance, that is, are better correlated than the pair of points at a larger separation. Autocorrelogram quantifies these relationships and allows gaining insights into the spatial behavior of the phenomenon under study. The point interpolation. A point interpolation performs an interpolation on randomly distributed point values and returns regularly distributed point values. The various interpolation methods are Voronoi, tessellation, moving average, trend surface and moving surface. Example, nearest neighbor, Voronoi tessellation. In this method, the value, the identifier or class name of the nearest point is assigned to the pixel. It offers a quick way to obtain a Tessinian map from point data. Summary. Spatial analysis provides a linkage between the real world and the GIS data. Spatial analysis can be done in two methods. One is raster based analysis and the other one vector based analysis. spatial analysis increases the capabilities of GIS procedures more efficient. We have discussed about different building blocks in spatial analysis, that is place, attribute, object, network, etc. We also discussed about the user of spatial analysis in the GIS and different statistical tools that are used spatial analysis. In the next chapter, we will discuss about the various raster and vector spatial analysis methods.